Rice cultivation is a crucial component of Bangladesh's economy and global food security, but it faces significant challenges from pathogens and climate change. To enhance rice disease classification accuracy, this study presents a novel approach integrating histogram of oriented gradients, HOG, and local binary patterns, LBP, feature extraction techniques. Gradient-weighted class activation mapping, Grad-CAM, is employed to identify critical regions within images, providing insights into the classification process. The methodology involves evaluating model performance metrics, including precision, recall, accuracy, and F1 score, following the integration of HOG and LBP feature extraction and Grad-CAM analysis. Notable improvements were observed across various models, including ResNet-50, ResNet-101, VGG16, VGG19, MobileNet v2, Inception v3, and EfficientNet b7, demonstrating significant advancements compared to baseline models. Performance metrics, detailed in tables I, II, and III, showcase the impact of HOG and LBP feature extraction on rice disease classification. The inclusion of HOG features notably improved F1 scores across different models, enhancing precision, recall, accuracy, and overall performance compared to baseline models. While LBP feature extraction demonstrated improvements, they were relatively lower compared to HOG extracted features. This research aims to contribute to more effective strategies to bolster rice cultivation and sustain global food security, particularly in regions like Bangladesh facing growing population demands. Researchers have explored the application of deep learning architectures, particularly convolutional neural networks, CNNs, for rice disease classification, achieving high accuracy rates in detecting and classifying prevalent rice plant diseases. Ensemble frameworks, transfer learning techniques, and novel CNN architectures have been employed to improve disease detection accuracy. For instance, Ahad et al. Achieved a 98% accuracy rate using an ensemble framework, while Singh et al. Proposed a tailored CNN architecture that demonstrated commendable accuracy rates with the Atom Optimizer. Bharanidharan et al. Utilized a modified lemurs optimization algorithm to enhance paddy disease detection accuracy, achieving a balanced accuracy of 90% for the k-nearest neighbor classifier. Comprehensive deep learning systems have also been developed for paddy plant disease detection, such as Haridasan et al.'s system, which achieved a high validation accuracy of 0.9145. KM et al. Compared 10 DCNN models for rice leaf disease identification, with exception net outperforming others, achieving a classification accuracy of 94.33%. Notably, Agarwal et al. Presented a lightweight federated deep learning architecture for rice leaf disease classification, ensuring data privacy and showcasing outstanding accuracy of 99% on both IID and non-IID datasets. Transfer learning has also been employed across 15 CNN models for automatic recognition of rice leaf diseases, with Inception v3 emerging as the top-performing model, achieving an impressive average accuracy of 99.64%. Optimized convolutional neural network architectures have been proposed, such as Pratasha et al.'s architecture, which achieved a notable validation accuracy of 98.7% with 16,770 collected images. Furthermore, Islam et al. Introduced a novel technique for rice disease identification through leaf image analysis coupled with an IoT-based smart rice field monitoring system, achieving a high accuracy of 98.7% and utilizing remote data collection for field monitoring and medication. A segmentation-based method employing VGG, ResNet, and dense net deep neural networks for rice leaf disease recognition has also been proposed, exhibiting promising performance with potential practical applications in agriculture. The proposed workflow for rice disease classification, as depicted in Figure 1, highlights the strategic utilization of feature engineering algorithms pivotal in the precise selection of optimal features within the workflow. This research focuses on developing a machine learning model for classifying rice diseases, including rice leaf blast, neck blast, and brown spot. The dataset consists of images from the rice leaf disease dataset and additional images from the rice leaves dataset on Kaggle, augmented using TensorFlow's Keras sequential model to enhance diversity and robustness. Feature extraction plays a crucial role in image processing and computer vision, as it elucidates and interprets image content. Two key feature extraction methods are employed: histogram of oriented gradients, HOG, and local binary pattern, LBP. HOG captures crucial image characteristics, such as edge directions and intensity, while LBP extracts texture features. The parameters for both techniques are carefully selected, including 9 orientations, 8 pixels per cell, and 2 cells per block for HOG, and a radius of 8 points, and the uniform method for LBP. The visualization of HOG features for brown spot disease in rice leaves demonstrates the technique's ability to capture essential image characteristics. By leveraging these features, the research aims to train a machine learning model capable of accurately classifying rice diseases. This could potentially aid in early detection and management strategies, mitigating yield loss and improving crop quality. The application of various convolutional neural network (CNN) architectures is investigated for image classification tasks, focusing on rice disease identification. The examined CNN models, including ResNet-50, Inception v3, ResNet-101, VGG16, VGG19, MobileNet v2, and EfficientNet v7, are prominent architectures that have driven advancements in computer vision. These baseline models are initially evaluated without feature extraction. ResNet-50 and ResNet-101 exhibit commendable performance with an accuracy of 91% and 92%, respectively. Both models display consistent precision and recall scores, highlighting their robustness. To assess the impact of feature extraction, the models are augmented with histogram of oriented gradients, HOG. The incorporation of HOG feature extraction results in marked improvements across all models. The most significant enhancement is observed in the EfficientNet v7 architecture, underscoring the potential for optimal feature extraction to bolster CNN efficacy in rice disease classification tasks. This comparative analysis demonstrates that the judicious selection of CNN architectures and feature extraction techniques can optimize image classification performance in the context of rice disease identification. Furthermore, this investigation showcases the capacity of deep learning to advance crop health monitoring and disease management. Key findings from this analysis include the merits of using suitable CNN models, integrating appropriate feature extraction, and their respective benefits in boosting performance and model robustness. Results of this investigation may serve as a starting point for developing targeted and advanced CNN models in various crop health and agricultural settings, but there are certain limitations inherent in using real-world agricultural images with their distinct varieties of complexities, underexposure to unchanging growth phases or instances and noise. Several unresolved avenues within agricultural science lend credence for adopting complex evaluation matrices, while this potential real-time feasibility merits diverse monitoring purposes where dynamic resource input options pose implementation trials amidst constraints typical within image retrieval functionality research with crops whose numerous breeds leave lots unsolved even without interpenetration limitations involved. So considering monitoring trends, image attributes coupled robust characteristics display room here open toward fresh concepts developing still after discovering aspects holding crops general deep structure general feasibility advanced practice today massage. The paper investigates the impact of feature extraction techniques, specifically histogram of oriented gradients, HOG, and local binary patterns, LBP, on the classification accuracy of rice diseases using convolutional neural networks, CNNs. It focuses on the performance enhancement achieved by integrating these techniques into various CNN architectures such as ResNet-50, ResNet-101, VGG16, VGG19, MobileNet v2, Inception v3, and EfficientNet v7. The results show that the addition of HOG significantly improves the accuracy from 92% to 97% in the EfficientNet v7 model, leading to substantial improvements in precision, recall, and the F1 score. In contrast, LBP has a more modest impact, with a notable improvement observed in the EfficientNet v7 model, where the accuracy increases to 90%. A comparative analysis with previous techniques reveals that the proposed method, utilizing efficient NET-B7 in conjunction with HOG descriptors, demonstrates the highest accuracy of 97%, outperforming other techniques listed in Table V. The paper also explores the neural network's decision-making process concerning rice disease classification through gradient-weighted class activation mapping, Grad-CAM. This technique provides insights into the regions within rice images that are pivotal for accurate disease identification without requiring architectural modifications or retraining of the CNN-based network. The visual representations in Figure 6 highlight the specific areas of interest within the images that contribute significantly to accurate disease classification, aiding in understanding the network's focus areas and enhancing interpretability and trustworthiness of the classification process. In conclusion, the study introduces and assesses advanced feature extraction methodologies, notably HOG and LBP, integrated within CNNs to enhance precision in rice disease classification. The findings underscore the pivotal role of feature extraction techniques, particularly HOG, in bolstering the classification performance of CNN architectures for agricultural disease identification systems. Rice cultivation is crucial for global food security, but various diseases affecting rice crops pose significant challenges. To address this, researchers have explored the potential of deep learning techniques, specifically convolutional neural networks, CNNs, for identifying and classifying rice leaf diseases. This study evaluates the performance of several state-of-the-art CNN architectures, including ResNet-50, Mobile Net-V2, and efficient Net-B7, in disease identification. Feature extraction techniques, such as histograms of oriented gradients, HOG, and local binary patterns, LBP, are also investigated to enhance accuracy. The findings indicate that the efficient Net-B7 model, when combined with HOG features, achieves the highest accuracy of 97%. This underscores the substantial efficacy of HOG in refining feature representations. Conversely, the integration of LBP resulted in a decrease in overall performance, suggesting it may not be as suitable for capturing relevant features in rice disease images compared to HOG. To enhance interpretability, the study employs gradient-weighted class activation mapping, Grad-CAM, which highlights crucial disease-affected areas within rice images. This not only aids in disease identification but also provides insights into the regions of the image that the model considers most relevant for classification. The paper reviews various datasets and techniques employed in previous studies on rice disease classification, emphasizing the need for more comprehensive and diverse datasets to improve model performance and generalizability. Optimized CNN-based systems have the potential to address challenges impeding global food security by bolstering rice cultivation. The use of optimized CNN architectures, combined with appropriate feature extraction techniques and interpretability tools, can significantly enhance the accuracy and efficiency of rice disease classification.